Nearly all of the global internet runs on Linux. But this vast, planetary-scale infrastructure traces its roots back to a college dorm room project created in the early 1990s. To keep modern servers secure, Linux relies on a strict internal border wall. At the top is user space, where regular applications live. Below that is kernel space, the highly privileged core that controls the physical hardware. Applications in user space can't touch the hardware on their own. If a web server wants to send a network packet or read a file, it has to send a request down to the kernel and wait for permission to cross that barrier. For decades, this strict separation worked perfectly. But modern cloud environments need to process millions of requests a second and adapt routing logic instantly. The kernel, by design, is highly rigid and difficult to modify. If you wanted the operating system to support a new networking feature, your best option was submitting a code patch to the Linux open source community. Even if they accepted your code, it could take years for that update to actually reach your production servers. The exact security architecture that protected the internet servers became the primary obstacle keeping them from scaling at the speed modern businesses required. Developers desperate to bypass this years-long wait turned to an alternative: kernel modules. These were custom pieces of code that could be injected directly into the core operating system on the fly. The problem is that kernel modules run with absolute unrestricted privileges. If a developer makes a single typographical error, that tiny mistake will trigger a kernel panic and crash the entire server globally. Cloud engineers were trapped. They had to choose between suffering crippling deployment delays for native updates or injecting volatile code that could cause systemic network outages. To solve this, the Linux community expanded a technology called eBPF, the Extended Berkeley Packet Filter. It acts as a technological bridge, allowing developers to program custom logic directly into the kernel without ever altering its official source code. Think of how a modern web browser works. 20 years ago, websites were static HTML documents. Then JavaScript came along, allowing developers to run dynamic programs right inside the browser. eBPF does exactly that, but for the operating system. The mechanism is a restricted sandbox built squarely inside the privileged kernel space. Before eBPF code enters, it passes through the Verifier, an automated gatekeeper that aggressively analyzes every instruction. If the code contains an infinite loop or a legal instruction, the Verifier instantly rejects it. Because the Verifier proactively neutralizes these threats, the risk of a system crash is eliminated. Developers finally get the extreme agility of kernel modules without the looming threat of catastrophic failure. Once verified, the code is attached to hooks, specific event-driven tripwires scattered throughout the kernel. You can trigger an eBPF program the exact millisecond a network packet arrives at the server, or the moment a specific user attempts to open a secure file. To share what it finds, the eBPF program uses maps, shared real-time data structures. Instead of clogging up the system with constant request and response traffic, these maps stream data directly from the kernel sandbox back up to user space. To ensure this happens instantly, a just-in-time compiler translates the verified instructions into native machine code. This allows the program to run at the exact speed of the hardware, with near-zero overhead. By combining event-driven hooks, real-time maps, and JIT compilation, the operating system gains a closed-loop system for interacting with its deepest layers safely and instantly. With the risk of system crashes removed and execution speeds matching native hardware, the world's largest tech companies have quietly used eBPF to replace the foundational layers of their infrastructure, often without ever rebooting a single server. In networking, companies like Meta use eBPF alongside a feature called XDP to intercept and load balance millions of global data packets before they even reach the main operating system stack. In security, modern defensive tools use the technology to monitor exact system behaviors in real time. They can instantly block malicious memory access at the kernel level before the threat executes, without degrading server performance. And for observability, companies like Netflix use eBPF to peer directly into thousands of containerized microservices, identifying obscure network bottlenecks with absolute zero blind spots. Across networking, security, and observability, eBPF has systematically replaced legacy infrastructure by giving engineers a direct, highly optimized line to the hardware. This technology redraws the physical boundaries of the operating system. It shifts Linux from a static gatekeeper into a fully programmable platform. For decades, software engineering operated on a strict trade-off. You could build a system for high performance, or you could build it for strict safety. That limitation is officially obsolete. By weaving extreme speed with absolute stability, eBPF gives developers the ability to safely rewrite and optimize the cloud from the inside out in real time.